We're going to cover sections 10.3 and 10.4 today. So section 10.3, apply properties to chords. Our objective is to use relationships of arcs and chords in a circle. Theorems. The first theorem we're going to learn today is in the same circle or congruent circles, two minor arcs are congruent if and only if their corresponding chords are congruent. Looks like this. So we've got, in this circle, we have the chords AB and AC congruent. Okay? So that means that the arcs AB and the arc AC would be congruent because those chords that intercept them are congruent. Any questions? Okay. Here's an example of how you might use this problem. We have to find the indicated measure BC. Yes? Yes. Go back, give you some more time to write that down. All right, everybody have it? Anybody need more time? Okay, now we'll do the example. So we have this circle. We're given arc AB is 116 degrees. We've got two congruent chords. Okay, so the first thing we know from that theorem is that these two arcs are congruent because the chords are congruent. What do I need to do to solve this problem? What would you do? We have to figure out the measures of arc AC and CB. What can we do? Aaron, what do you think we would do? Not sure? Go ahead, Logan. Yes. We have to figure out how much is left of the circle outside of this 116. So we would take 360 minus 116. All right? So that's you've got 244 left, right? And then you're going to divide that by 2, and you get 122 for each of these arcs, right? Any questions? No questions. Okay. Mr. Moore. All right. Yes, I do. Yeah, should he just bring his stuff or he could come back? Okay. All right. Yep. Devin, you need to go see Mr. Walpole down in the office, the dean's office. You don't need to take your stuff. He said you'd be back. So. All right. Next theorem. If one chord is perpendicular to another chord, then the first chord is a diameter. Looks like this. Okay, so we have JD perpendicular to AB, right? So we know that JD has to go through the center of the circle. It's the perpendicular bisector of a chord. We had that last time, right? We know the perpendicular bisector of a chord goes through the center. So JD has to be a diameter. It's this kind of is an extension of that perpendicular bisector theorem we learned last time, right? Just rather than saying JD goes through the center, they are saying that we're going to call JD a diameter. Everybody have it? Okay. Example. Find the value of x. Find the value of x. What would we do to find the value of x? And tell me why. Why would we do that? Carly, what do you think? What would we do to find the value of x?
Set them equal to each other.
We set them, and what?
And then find x.
Okay, and solve for x. How do you know that you can set them equal to each other? What tells you that?
Bisector.
Well, we're not given that it's a bisector, but we know it's a bisector because of what? The right angle and going through the center. Remember we talked about two of the three things? If you've got a perpendicular bisector, we've got three things going on. We've got it's going through the center, we've got it's perpendicular, and we've got it bisects. If you know two of the three of those, then you know the third. So in this case, we know perpendicular and through the center, so we know then it bisects. So as Carly said, these two segments are equal, so we're going to set those equal each other and solve. So we set 12x plus 7 equal to 3x plus 16, and we solve. All right, so that's going to, we can go ahead and solve that. 9x is equal to 9x equals 1 is our answer. Any questions on that example? All right. If a diameter of a circle is perpendicular to a chord and the diameter bisects the chord, then the diameter bisects the chord and its arc. So we're adding on to this perpendicular bisector idea. Not only does it bisect the chord, it bisects the arc. So we could say that arc AD is congruent to arc DB. The chord that intersects that arc AB is bisected, so arc AB will be bisected by the segment JD as well. Any questions? Okay, everybody have it? All right, moving on. Example. Find the indicated measure. PQR. Make sure you notice what they're asking for. They're wanting PQR, so they're wanting the length, the measure of this entire chord, PQR. What would that be and why? Seth. What? It would be 80. Why? How did you know it was 80? Okay, right. Both sides are congruent. PQ is 40, so we know QR is 40, and then we add those two together, and we're going to get 80, right? 40 degrees plus 40 degrees equals 80 degrees. right? Or you could have taken 40 times 2. Any questions on that example? All right. In the same circle, or in congruent circles, two chords are congruent if and only if they are equidistant from the center. Looks like this. All right. We can say that the chord AB would be congruent to the chord CD. This congruent marking is for the entire chord, not just AE and CG. It's for the entire chord, right? We could say that is true, or that happens if we know that EF, this chord from the center to the chord AB, if we know that distance is the same as FG. If those two distances are the same, right? FE and FG, if those two distances are the same, in other words, the chord's the same distance from the center, then we know those two chords are going to have the same length. Chord AB and chord CD are going to have the same length. Questions on that theorem? All right, everybody have it? Okay, moving on. Here's the example. We have the circle as marked. We have to determine x. How would I do it? Let's see, Jacob. Oh, Jacob, go ahead. What would I do?
You would put them together, or you'd equal 3x minus 11 equals x plus 9.
Right, and how did you know to do that?
They both have right angles.
And they're both right angles, and what else?
Congruent.
Right, they're both congruent. Why do they have the right angle there? What does that tell you? What does that tell you? Why does that need to be a right angle? Kennedy, what do you think? Why does that need to be a right angle?
I'm not sure.
Okay, because the shortest distance from a point to a line is on the perpendicular, right? From that point to the line. If we didn't have this right angle, then this line could possibly be going over this way if I exaggerate it, and that wouldn't be the distance. The distance between the point and the line is the perpendicular distance. So that's why they have that. You have to look for that right angle to make sure you know that that's the distance. So those distances from the point to the lines are the same. So as Jacob said, we would take 3x minus 11, and we would set it equal to x plus 9, and then we'll solve for x. So I solve for x, we've got 2x equals 20, so x equals 10 would be our answer. Any questions on that? No questions. Okay. 10.4. We're going to use inscribed angles and polygons. We're going to use inscribed angles to find arc measures. Okay, so we defined inscribed angles before. Now we're going to use them to find arc measures. I'm getting disconnected here from the computer. Let me see if I can get it reconnected. Come on, okay. Vocabulary. Inscribed angle. Angle whose vertex is on a circle and whose sides contain chords of the circle. So in this picture, angle ABC is the inscribed angle. The vertex, angle B, is on the circle, right? B is on the circle, and the sides contain chords. We've got the chords AB and CB. That is an inscribed angle. All right. Everybody got it? All right. Intercepted arc. The intercepted arc is the arc that lies in the interior of the inscribed angle and has endpoints on the angle. In this picture, the inscribed angle is arc AC. It's always going to be the minor arc. You wouldn't go the long way around and call it an inscribed angle. It's always the minor arc that's going to be intercepted by the inscribed angle that's going to be your intercepted arc. Everybody got it? All right, moving on. Inscribed polygon in a circle. All of that would look like something like this. It's all of the vertices of the polygon lie on the circle. So this is a pentagon. This pentagon is inscribed in the circle because all its vertices touch the circle. The circle is said to be circumscribed about the polygon. So the polygon is inscribed in the circle, and the circle circumscribes the polygon. Hi.
Good morning.
Come on
Do you
in.
mind if I come in?
Yeah, sure.
Thank you. Sorry.
All right. So we've done inscribed triangles, right, when we did the circumcenter. Same idea, but this is a polygon instead of a triangle. All right. Some theorems involving inscribed angle. The measure of an inscribed angle. If an angle is inscribed in a circle, the measure is half the measure of the intercepted arc. It's half the measure. So angle B would be half of arc AC. Now before we talked about central angles, right? If we had a central angle here that inscribed AC, what would its measure be compared to the arc? Central angle. You did this on the quiz we just took, right? There's your central angle. What's its measure compared to the arc? Central angle. Kaylee. Anybody? Central angle? Okay. Kennedy, what's the central angle? Okay, it's the same. Central angle is the same as the intercepted arc. The inscribed angle is half. The inscribed angle would be the blue. It's half. Don't confuse that, okay? Make sure central angle is the same. Inscribed angle is half the intercepted arc. Don't get those confused. All right. So here's an example. If B, measure of angle B is 30, then we know that the arc AC is 60. It's twice. Because B is half of AC. All right, any questions on that one? Everybody have it?
We may have done ganging up on you now.
Oh, yeah, double teaming, huh? All right. Okay, moving on. If two inscribed angles of a circle intercept the same arc, then the angles are congruent. If two inscribed angles of a circle intercept the same arc, then the angles are congruent. So it looks like this. Okay, we have, in this picture, we have angle BAD, the red angle, and angle BCD. They both intercept this arc, BD. Okay? If they both intercept BD, I shouldn't have marked that out. If they both intercept BD, then we know angle A is congruent to angle C. Right? Those two angles are congruent. They may not look like it. It's kind of deceiving. When you look at this picture, it kind of looks like A is bigger than C, just because of the way the angles are spaced out. The chords are spaced out. But, trust me, they have the same measure. I mean, they are both half of BD. They are both half of BD. All right, everybody have that? Okay, moving on. Some more examples. Everybody get that written down? Did I go too fast? Everybody got it? Okay, some more examples. Find the measure of the indicated arc or angle. What would the measure of BC be? According to our new rule, Abby, what would BC be? Wouldn't be half, it would be
76.
twice. It's double. The arc is twice the inscribed. So it would be, we would take 38 times 2 equals 76 degrees, right? So that's 76 degrees. What about this second one? What would arc BC be? What's that? Okay, we multiply times 2, so 78 times 2. What is 78 times 2? Mental math. Anybody do that in their head? 78 times 2? Yeah. 156. Good. 78 times 2 is 156. You take 70 times 2, that's 140. And then you take 8 times 2, that's 16. You add them together, you get 156. Mental math. All right. Any questions on that? Okay. More theorems. We're almost done. More theorems. 10.9. If a right triangle is inscribed in a circle, then the hypotenuse is the diameter. That makes sense, right? Because if this is a right triangle, then it intercepts this arc. That arc would be twice. If this is 90, this would be 180. We know 180 is half a circle, half of 360. So this line divides the circle in half. It's got to be the diameter. It's got to be the diameter. Oh, okay. Next theorem. A quadrilateral can be inscribed in a circle if and only if its opposite angles are supplementary. Looks like this, right? The only way this quadrilateral is supplementary, is inscribed in the circle, is if A plus D equals 180 and if C plus B equals 180. And if you think about it, that makes sense because all the way around a circle is 360, right? So if we, take for instance the A and D, if we draw the line across from A to D, it's not the diameter, but, oh no, wait, I drew the wrong line. If we draw the line across here from B to C, it doesn't necessarily have to be the diameter, But we know that A does this part of the circle and D does the other part of the circle. So together they would have to be, when they add those two parts together, it's 360. So the sum of these two would have to, the angles would have to be 180. All right? So the angles across from each other when the quadrilateral is inscribed in the circle equals 180. Any questions? Everybody have it? All right. Some more examples. Describe whether the polygon can be inscribed in a circle. All right. What do we have to do to tell if the polygon can be inscribed in the circle? What would we have to do? We have to find this angle first, right? Before we can tell these sum to 180, we have to find this angle. How am I going to find that angle? What did the four angles of the polygon add up, of the quadrilateral add up to? Four angles add up to what? Quadrilateral? 360, right. So we take 360 and we subtract 70, 92, and 130, right? So we're subtracting 292 from 360, so that would be 68, right? If I did my math correct. 292, yeah, 68. So if this angle is 68, could that be inscribed in a circle? Brandon says yes. Anybody else have opinion? All right, we have to add these two together. They're supposed to equal 180. That was our theorem, right? They have to be supplementary. So 92 plus 68 equals 160. It does not equal 180, so the answer is no. That one wouldn't work. Okay? That one would not work. All right, number 2. We have, it looks like a kite, right? We have a kite. So, what do we do here? We know, what do we know about these two angles? This angle and this angle. What do we know about them in a kite? They're congruent. So how can I figure out what their measure is? $360 minus 180 and 130 and 50, right? 360 minus 130 and 150. That's 180. We divide that by 2. They're both 90, right? Both of those are 90. So,
yes.
you can, because we had 90 and 90. That's 180. We had 130 and 50. They're 180. So the answer is yes. 90 plus 90 equals 180, and 130 plus 50 equals 180. All right. Any questions there? Okay. So we have some more examples. Because of time, I'll just work through these quickly to help you solve this. Okay. So we've got here. This is a right angle. Okay, this is a right angle, so that means that x would be 180. If x is 180, and these two chords are congruent, they're going to be equal to each other, and they're going to equal y plus y equals 180. So that means y equals 90. Y would equal 90 degrees on number 1. Number 2. X and Y both inscribe the same arc. right? That arc is 110. They're both half of 110. X and Y equal 110 divided by 2, so they both equal 55. Right? Then on the third one here, this quadrilateral is inscribed in the circle, so we know the opposite angles are supplementary. So we would take 105 plus X equals 180, solve, X equals 75. All right? Any questions on those? Okay, that's it on the notes.